discuss the terminology associated with kinematics. So we're going to go through a whole sequence of basic definitions so that we're speaking the same language. The word magnitude means size, how big anything is, the magnitude of acceleration, the magnitude of magnetic field strength. We've been using this word in many different contexts. The word negligible means so small that it can be ignored. So if I say that there's negligible air resistance, it just means don't worry about it. Don't take it into account. Instantaneous means that it happens in such a small time period that time is effectively zero. Of course, that never really happens, but we can get instantaneous by shrinking that time period smaller and smaller. Objects that move together have the same speed. So if you're in an airplane going 600 miles per hour, then you're going 600 miles per hour, even though while you're in the airplane, it doesn't seem like you're moving at all, because you're not relative to the airplane itself. So if you're holding a ball and you drop it and you're standing still, then the ball is standing still. If you're walking and you drop the ball, then the ball has the same initial speed as you do. There are only 4 types of motion that we're going to be talking about. There's at rest, or not moving. There's constant speed, which means you're not changing the rate at which you're moving. You're moving with increasing speed, or you're moving with decreasing speed. And we're going to spend a little bit of time exploring what all of that really means, but you have to know that those are the only 4 types of motion. So every time I ask you, what type of motion is it? It's a multiple choice question. There's only 4 choices: at rest, constant, increasing, or decreasing. Vector quantities have a size and a direction. Scalar quantities have magnitude only. So when I say that I'm moving at 3 meters per second, that's speed, which is a scalar quantity. If I say I'm moving 3 meters per second west, so I gave it a direction, that's velocity because it's a vector quantity. A position is a location relative to some origin. The origin needs to be defined, and sometimes you get to define it, sometimes the problem defines it. It's communicated by using a coordinate, generally speaking, and the symbol can be X or Y generally, because we're using coordinates, although there are other symbols that we may use as well. All distance measurements, positions are in the metric system in meters. Distance is the amount of space between 2 things. However, it's also the total amount of ground you've covered. So you may find that, you travel not in a straight line. It's not just the distance between those 2 endpoints. That's actually displacement, which we're going to talk about next. Distance is the total amount of ground you've covered, and it depends on the path you take. Displacement, the path doesn't matter. It's path independent. What matters are the 2 endpoints. So you can find the displacement by subtracting your 1 endpoint from your beginning point, and you'll get the overall change in position. The symbol for displacement is generally delta D, delta X, or delta Y. For distance, we just use a D, generally speaking. The units for all of these are in meters. So when you look at this diagram here, you can see the displacement is the straight line change from your beginning point to your end point, where the distance traveled, right, is this whole path. Let's contrast speed and velocity. We tend to use these terms interchangeably. They're very similar, but there's one big difference between them. Speed depends on distance, velocity depends on displacement. That makes speed a scalar quantity and velocity is a vector quantity. Speed is how fast you cover a distance, whereas velocity is how fast you change your position. Symbols are the same and the units are the same. When we talk about constant speed, acceleration is 0. You do not change your speed or velocity. When we talk about instantaneous versus average, an average velocity is your total distance divided by your total time. So that's the average, right? And it's not taking into account the little changes that happen from moment to moment. Instantaneous velocity is any smaller segment of that average velocity. So if my average velocity is taken over an hour, an instantaneous velocity might be how fast am I going in the first minute or in the 30th minute, like that. If I'm taking a really long trip, like down to Orlando, I'm covering 1,000 miles, an instantaneous velocity might be how long it took me to go from exit 168 on the parkway to exit 160 on the parkway. That velocity that I'm doing, that's more instantaneous than that 1,000-mile trip. The signs of velocity depend on which way you make positive. So when we talk about direction, we give something a sign. And we make up, okay, to the right is positive, east is positive, up is positive, therefore down would be negative, west would be negative, to the left would be negative. I mean, these are things that we will discuss and determine ourselves. And it's all relative. It's just a shorthand way of saying, I'm moving in the positive direction. So we say, oh, I have a velocity of positive 3.1 meters per second. If I say I have a velocity of negative 10 meters per second, it just means I'm moving opposite the direction I'm saying positive is. We define which way is positive. Acceleration is when that velocity is changing. The symbol is little a and the units are meters per second squared, which you'll also see written as meters per second per second. The equation for it is the change in velocity over the change in time. It's not v over t, it's delta v over delta t. That delta means change, and it's really important, so don't ignore it. You can change your acceleration in two ways. The first way is to change your speed. The second way is to change your direction. You can also change both, but one of those things has to change. In this unit, we're going to focus on changing your speed. That's when things accelerate. It's because we're only doing linear motion or straight line motion, so we will not have changes in direction. We'll talk about changes in direction when we talk about circular motion. In this course, please note that we only do constant acceleration. We are not going to talk about changing acceleration because you need to be able to do this stuff with calculus in order to deal with those types of changes. So let's just flesh out what acceleration means, because it's kind of we don't see acceleration. We know when it's present, you can feel it, but what does it actually mean? So if I said 1 meter per second squared, that means I'm changing my speed by 1 meter per second every second. So every second, so if I start at rest, that first second I'm going 1 meter per second, the next second I'll be going 2 meters per second, the next second I'll go 3, etc. So I'm adding on 1 meter per second every second. What does it mean if I'm going negative 1 meter per second squared? Well, if I start at rest, that means the next second I'll be going -1, then -2, then -3, which means I'm moving backwards. If I say I'm starting at 10 meters per second with an acceleration of -1 meter per second squared, that means that in the next second I'm going 9, then I'm going 8. So I'm taking away 1 meter per second every second. So let's talk about a very specific example of an accelerating object. We're going to discuss free fall as a special case. It applies to only one particular type of problem, but it comes up so frequently that it's really worth spending a few minutes discussing. Free fall is defined as an object acted upon only by gravity. There can't be anything else touching the object. We always ignore air resistance. And even though the name is free fall, an object can be rising or it might be falling. So don't be deceived by the name. It does not only cover falling objects. However, it does mean that we're only moving vertically up and down. You're not moving horizontally. Acceleration due to gravity has the symbol little g or a sub little g. I'll generally use g. And g is a constant. It's on your equation sheet. It's equal to 9.8 meters per second squared. It does not have a sign. It's a constant value, although it changes based on location, but only by a little bit. So generally, we're just going to say at the surface of the Earth, acceleration due to gravity is 9.8 meters per second squared, as it only changes very little due to altitude. In free fall, the sign of acceleration due to gravity is -g because the Earth is always pulling down. So that downward vector, we define it as negative. But g itself is a scalar quantity. It's 9.8. Acceleration due to gravity, a sub g, is -9.8 meters per second squared, but it's only for an object in free fall. So do not ever use it for anything else. A few other important things to remember about free fall. The word drop means initial velocity 0. Throw means your initial velocity is greater than 0. At maximum height, the instantaneous velocity is 0. It stops for a moment, like it's not moving up anymore, but it's not yet moving down. So at that one moment, velocity is 0. There's a symmetrical trajectory. Trajectory is just a fancy word for path. That means that on the way up, the velocities are the same at the exact same positions, but they have opposite signs, right? And it takes the same amount of time to go up as it does to go down. So those things make it a symmetrical trajectory. When we say an object hits the ground or strikes the ground, it's not in free fall anymore. So if you see a question that says, how much time did it take to strike the ground? What's the velocity when it strikes the ground? We actually mean the micrometer right before it hits the ground while it's still in free fall. Because don't forget, once it hits something, once there's another force acting on the object, it's no longer in free fall. So we can only take that moment right before it hits the ground. So the final velocity of an object in free fall right above the ground is never 0 because it's at maximum speed at that point. And last, free fall is independent of mass because we ignore air resistance, and air resistance and mass are highly related, but we're not going to pay attention to that in this unit. And here are some really helpful websites. Feel free to visit them, especially the physics classroom. They get some great interactives. I highly recommend.